Assalamualaikum warahmatullahi wabarakatuh. I am Ariff bin Awang Rahman and my matrix card number is 2019725581. My final year project is on the design of a portable curve projector screen for Postura Motergo indoor motorcycle simulator facility. My supervisor is Dr. Helmi bin Rashid with the help of a co-supervisor Dr. Wan Muhammad Syahmi. So basically, what is my project about? In summary, my project is, as the title says, is on designing a portable curve projector screen for Postura Motergo indoor motorcycle facility. It is located at the Motorcycle Engineering Technology Laboratory, or METAL for short. Postura Motergo is a simulator that houses the pillion simulation system with the purpose of filling the gap in the research regarding pillion on motorcycle riding, since most of the research on motorcycles focuses more on the rider rather than the pillion. The system consists of a few integral parts that complete the simulation system, such as a mock motorcycle with pillion features, audio-visual elements, wind blast elements, and vibration elements, and motion system. The chassis was built from scratch so that it can be adjusted to the multiple riding position of different types of motorcycles. The audio-visual element consists of a curved screen, which images are projected by 3 projectors. The different images from the 3 projectors are combined to make one big image by the use of a mapping and warping software called Immersive Calibration Pro by Fly Elise. The curved screen is made by using plywood and formica as the main materials. The screen itself is fixed to the facility. Next, we have the wind blast element. It uses a set of industrial blowers in front of the motorcycle to simulate the sensation of wind blowing when riding a motorcycle. The vibration system for the simulator uses a device called Park Kicker Gamer 2. This device simulates the bumps on the road when using the simulator. Lastly is the motion system. The motion system uses a DC servo motor at the roll axis to simulate the roll of the motorcycle. Since all of the simulator's equipment are plug and play, the screen hinders the ability for the simulator to be moved anywhere since it is permanently fixed to the facility. There are also some third parties that are interested in renting the simulator at an external venue. With the simulator being affixed to the facility, the laboratory has to turn down the offer. This causes a lot of missed opportunity for the facility. Therefore, this project aims to solve this problem by designing a new screen that is portable for the use case of this motorcycle simulator. Research on the previous design for the portable curved projector screen was done in order to find any design that would help in developing the design for this project. Through searches on Google Patterns using a combination of keywords such as curved projector screen, curved portable projector screen, and curved portable projector screen, there are currently limited designs that will fit the use case of this project. However, there are 2 patterns that are notable. The first pattern is from Starkweather, where it is an invention of a curved projection display that uses 2 or more rear projections for creating immersive environment. The rear projection will project onto a translucent display with the distortion being corrected optically while being projected onto the screen. Meanwhile, the other pattern is a pattern on a portable projection screen which focuses on the portability of the projection screen. The projection screen is a flat rather than curved. The pattern uses flexible projection screen held by a roller in which the screen is encased in a housing that can slide to collapse the projection screen. What this project needs is a curved portable projection screen. But why use a curved projection screen? The curved screen was introduced in the year 1937 at the International Exposition in Paris. The idea of using a curved screen for projecting media was not commonly used until it was used by Cinerama. Cinerama inventor Fred Waller conducted a research on the curved screen and concluded that the curved projection screen increases the immersiveness of the viewer by including the image in the viewer's peripheral vision. This makes the viewer feel like they are right at the center of the image rather than viewing the image on a screen. But there are now widely available consumer products that are used to simulate virtual realities. The most common approach in displaying images in simulations are through either head-mounted displays, monitors, and large projection screens. The most immersive experience was found to be using the head-mounted displays and large projection screen. However, there are no significant difference in immersiveness when comparing between the 2 methods, as both of them shows the same level of immersiveness. The cost of a head-mounted display are significantly higher than a large projection display. Most head-mounted displays are wired, which would hinder any movement from the observer. Therefore, a large projection display shows more promise while being way cheaper than using a head-mounted display. Moreover, since the use case for this project is for simulating riding on a motorcycle, the use of a helmet is required. This would mean that there is no way to wear the VR goggles. The development of the portable curve projection screen should take into consideration the human ergonomics while riding the motorcycle to ensure it closely simulates the riding experience of the motorcycle. The screen would consider the vision of the rider while wearing the helmet. The minimum peripheral vision allowed for a helmet is 120 degrees, and the riding height of the rider should be taken into consideration. The average ride height of motorcycle riders in Malaysia is 1.43 meters at eye level from the ground. Coupled with the additional height by the simulation system of Postura Motergo, the middle point of the screen should be around 1.5 meters in height. Based on what has been said, there are currently limited design of a portable curve projection screen. The existing designs are either curved or portable. There is no design that incorporates the two together. Therefore, to fulfill the need of the Metal Labs Postura Motergo indoor motorcycle simulator, a new design that considers both criteria is needed. Therefore, the objectives of this project is to determine the design parameters of the portable curve projection screen, to design the portable curve projection screen based on the determined parameters, and to analyze and validate the design using computer-aided design and computer-aided engineering. The scope of this project is to design a portable curve projection screen for Postura Motergo motorcycle simulator. The project should be limited to the design of the screen for the motorcycle simulator. Therefore, the design of the screen should take into consideration any relevant specification of the simulator itself. On top of that, with the ongoing movement control order due to the COVID-19 pandemic, the project is limited to online pictures of the simulator, online discussion with the members of the Metal Lab, and the journal for the motorcycle simulator as a source of information for this project. The method used for this project is the design process. This includes the problem definition, information gathering, concept generation, concept selection, product architecture, detailed design, computer-aided engineering, engineering drawing, and bill of materials. This is the flowchart of this project which spans between FYP1 and FYP2. FYP1 will cover the problem identification, information gathering, concept generation, concept selection, and preliminary design on top of this proposal presentation and documentation. As for FYP2, the project will continue with the design process with the product architecture, detailed design, computer-aided engineering, engineering drawing, and bill of materials. And this is the Gantt chart for the FYP1 which have been completed during this semester. The Gantt chart shows my progress in this project along the semester from week 1 until week 14. Most of the problem identification was made through speaking with the metal personnel which voiced their opinions on the existing projection screen. The information was gathered and was used as the design goal for this project. The main problem with the current design of the projection screen is that it is permanently fixed to the metal laboratory, which causes more problems such as it cannot be rented to a third party at another location for profit. The metal laboratory cannot be moved to a new facility, and the screen was made from plywood and metal, which was a cost-saving measure in the early development of the simulator. The product on the market was taken as a benchmark when designing the projection screen. This product was taken from an online marketplace called EC21. The product will act as a design benchmark for this project. Using the gathered information, a product design specification was developed. The PDS helps to address the needs of the metal laboratory with the design of the project. The PDS for this project is the product is to be used as a projector screen. The screen must maintain a recognizable screen ratio. The height from the ground level to the middle of the screen is 1.5 meters. The screen is curved at a radius of 1.5 meters. The screen has a 120-degree field of view. The product can be disassembled and reassembled. The disassembled parts must not exceed 2 meters in height and length. The idea for this project was sketched in order to document the ideas for it to be considered in the concept generation. Some of the sketches were used in the concept generation while some were scrapped as the product design specification evolved. The method used for concept generation is by using morphological charts. 3 concepts were generated using the morphological chart. The chart shows the components selected when developing the concepts. Some of the concepts were inspired by real-world items. The type of mounting for the screen was inspired from the rod from a tent, a banner, a curved plywood, which is currently being used by Metal Laboratory for Postura Motergo projection screen design. 3 concepts were generated from the morphological chart by selecting and combining the components. The 3 concepts were sketched by hand and developed in computer-aided design software, which is SolidWorks, to properly assess the design of each of the concepts. The concepts are as follows. This is the CAD model for the concept 1. The standing column was combined with a cross base and curved rod for the screen type, while for concept 2, the standing column combined with a cross base and combined with a curved plywood. Lastly, for the third concept, we have an interconnected design combined with a cross base and rope secured canvas design. Now that there are 3 concepts for the project, only one design concept would be selected to be used in this project. The selection of the concept was done through using a pew chart. The pew chart was used to compare the concept with the benchmark design to find the design that is not only better than the benchmark design, but better than the other concepts. The concepts were compared to the benchmark on the different characteristics. The benchmark acts as the datum point for the evaluation of the other 3 design concepts. The overall score determines the best concept design for the project. Based on the pew chart, the best score for the design of this project is the concept with a score of 3+. The design concept selected is concept 3, which scored a 3+ with positive in ease of disassembly, stability, rigidity, and portability. On the other hand, the design scored a 1- in the characteristic of manufacturing complexity when compared to the benchmark design. It also scores a neutral in the ease of assembly and safety, which means that the design is the same with the benchmark, and the design was selected because of the strength it has when compared to the other 2 concept design, as well as the compared with the benchmark design. The selected design has similar features to the benchmark design, but with the innovation of adding portability to the design by dissecting the structure into sections that can be disassembled. The foot base of the design was also changed from the benchmark to accommodate the different sections that can stand alone when disassembled. The base was redesigned to give a large surface area to increase stability. The structure, when fully assembled, will be secured by the same rope that is used to secure the canvas screen to the structure of the portable curve projection screen. As proof of concept, here is the design of the projector screen in SolidWorks, which shows the ability of the screen to be disassembled and reassembled for portability. The preliminary design will be used in FYP2 for the continuation of the project, where the design will move on to the next stage in the design process. The detailed design analysis, and bill of materials for the design will be made on FYP2. The design will be tested on the simulation and the results of the testing will be analyzed. The cost analysis for the design will also be taken into consideration in FYP2. The design will be analyzed with a finite element analysis using SolidWorks. This analysis will be used to understand the real-world effect on the design of the screen. After that, the bill of material and the engineering drawing for the design will be developed. The planning for FYP2 can be seen in this Gantt chart, which shows the continuation of the design process to complete this project. With that, that is the end of my presentation, and I would like to thank you for your time.